Good morning, everybody. You know it's early. This morning session was on quantum simulation. I'm Randy Hillett and Kirsten Rice. And our first speaker is Eugene Demler from UCH Zürich. And Eugene will talk about kinetic, magnetism, and electron systems and quantum simulators. Eugene?
Okay, well, it's a pleasure to be here. Many thanks to the organizers for bringing together this great conference. Yeah, I'll tell you about the work we have been doing on an unusual type of magnetism, which I will explain. Actually, I realized maybe, did I turn it on? Yes, okay, now it's on. And I want to begin by acknowledging people who did all the real work here. So the main credit should go to Ivan Marrera and Lukas Homeyer. And also it builds up on the earlier work which we have done with Yao, Annabelle, and Fabian. And what made this work particularly exciting is collaboration with our experimental colleagues. So I'll show you some of the results from Wasim's experiments. Also show you results from recent experiments in Antoine Bravet's group, and also Marcus and Attach's experiments. And there was also an earlier experiment in Wim van der Sijpen's group, which sort of I will use to illustrate some of the ideas. So this is the sorry. Okay, there's a typo. So the first line is supposed to be not obviously kinetic magnetism twice. I'll just start by reviewing some of the unusual magnetism that has been seen in Moira lattices of transition metal dicalcogenides. And I will use, in order to explain this unusual magnetism, we'll talk about the idea that first goes back to Nagaoka of magnetism arising from the motion of charge carriers, and he considered it in the case of the square lattice. Then we will move to see how it gets modified in lattices with frustration, specifically triangular lattices. And here the original idea, the first time this analysis was done was by Harter and Shastri. And then I'll talk about experiments which have explored this phenomena in quantum simulators. So this will be quantum gas microscopes and then Rydberg arrays. Okay, so during the last few years, there has been a lot of interest in lattices beyond the square lattice, motivated to a large extent by Moira systems, and sort of our experimental colleagues in the cold atoms community also got intrigued and realized triangular lattices in the experiments, and I hope we will hear more about this in Wasim's talk. And there are many kind of interesting experimental puzzles in Moira materials. I will highlight just one, which is central to what I'll be discussing. So these experiments in Cornell, and they were looking at magnetism close to the mode insulating state at n=1. And they chose to represent spin susceptibility in these Curie-Weiss ansatz. See that the theta actually represents the effect of interaction. So this form is kind of designed usually to describe magnetism of localized magnetic moments. So when theta is 0, we just have 1/t susceptibility of non-interacting spins, localized spins. When theta is positive, well, then susceptibility is enhanced. So we're talking about ferromagnetic interactions. And when theta is negative, then we have anti-ferromagnetic interaction, which suppress spin susceptibility. And what is plotted here is basically minus theta. And you can see that within the error bar, theta is equal to 0. And then as they dope the system, they see that on the double doped side, they see effective ferromagnetic interactions. And on the hole doped side, they see effective anti-ferromagnetic interaction. So this really goes contrary to the intuition that we have developed over the years, let's say for in the context of square lattices, where the strongest magnetism is expected to be exactly at half filling for n equals 1, and as soon as we dope, magnetism gets suppressed. Here you can see that magnetism appears when the system is doped, and also the sign of doping is important. Then similar results have been obtained in the group of Atachi Mamoglu. However, that's also basically spin susceptibility. However, in their case, they do not see the anti-ferromagnetic part, anti-ferromagnetic interaction, and hence changes related to anti-ferromagnetic interactions on the hole doped side, but they see kind of increase of susceptibility, kind of active ferromagnetic interactions close to when the system is double and doped. And you can say, oh, well, maybe it's because of Van Hove singularity. Interestingly, this effect disappears when the filling factor comes close to being Van Hove singularity. So it's very different from traditional Stoner instability, which obviously would be strongest at the Van Hove singularity.
The material for
I don't think I'll be able to tell you right away. I mean, these are different materials, like in attaches and so yeah, sorry, we can look it up. Okay, so let's take a step back and think about the original idea of Nagaoka of kind of non-super exchange mechanism of magnetic order. So like when we think about super exchange interaction, we all remember it's anti-ferromagnetic, it's T squared over U. And so if we have a lattice, then we basically say that every bond, like if the system develops anti-ferromagnetic order, there is a gain of T squared over U per site. So therefore the energy gain scales with the system size. And then Nagaoka said, well, now let us consider a situation when we introduce one hole and ask what is the optimal spin configuration for the hole to propagate. And you can show that like one particle propagates most efficiently if all the spins are pointing the same way, then different trajectories. Then if a hole propagates on different trajectories, there can be constructive interference and the hole gets the lowest kinetic energy. And then more or less, Nagaoka played a trick. He said, well, let's keep the system size finite and take U to infinity. Then for any finite n, right, okay, super exchange vanishes, and therefore like the energy gain due to the motion of the hole wins, and we get ferromagnetism. You can argue that, well, maybe it's not very physical, but let's say in finite size system, one can do this. And so this is the experiment from on der Seipen's group and theory done by Yao, when they took like a plaquette, 4 quantum dots with 3 electrons, and showed that by changing effectively interaction versus tunneling, they could see a transition from the lowest energy state being spin polarized 3/2 to then switching to the state which has a lowest possible spin, which is 1/2. Okay, so now let me remind you of another idea, and this is the idea of frustration. So usually we think about it in the context of anti-ferromagnetic interaction. Say, having a triangle, neighboring spins want to be anti-aligned, but then of course we cannot accommodate all sort of this anti-ferromagnetic arrangement for all 3 bonds. Well, there is another frustration that you were familiar with, and this is when particles move in the presence of magnetic flux. So take a simple example of just a particle moving in a plaquette, and we're asking how it moves from one corner to the other. It can either go through the upper path or the lower path, and in quantum mechanics, we need to add the amplitudes. But if there is a flux through the plaquette, and especially if this flux is of the order of pi, then there will be strong destructive interference. And this is what underlies, say, flat Landau levels, right? Destructive interference of different trajectories. But do we need to have external flux in order to see frustration? Well, let me show you that this doesn't have to be the case. So imagine a situation, and we start with a triangular lattice. Like, let me keep my life simple. I'll just consider like a zigzag ladder. And I also start with a system which has been polarized, and I introduce one hole. And now let me consider how this hole moves just by one side. So the first thing that we recognize is that if we want to talk about not the original electrons, but holes, because we have just one hole, it's a more efficient language, we have to exchange creation and annihilation operators, right? And therefore what used to be kind of hopping term for the electron, now that when we turn it into the hole operator, acquires an extra minus sign. So the motion of the hole actually, like tunneling, has opposite sign. And now we recognize that on a triangular lattice, this can make a big difference, right? Because if the hole moves once, okay, we get sort of minus sign from a strong sign of tunneling. But if it goes on the upper trajectory, we get minus sign squared, which of course becomes plus, and therefore upper and lower trajectory actually also interfere destructively. It's not completely destructively, but there is suppression of the propagation. So as a result, if one takes the dispersion of one hole, right, in the spin polarized band insulator in a zigzag ladder, one finds something interesting, that the bottom of the band is actually not as low as the bottom of the band if this was a bosonic system. And roughly, we usually say that the bottom of the band for tight binding should be kind of tunneling times the number of nearest neighbors. And that's true for the bosonic systems, the bottom of the band at minus 4T. But for the hole in the fermionic system, you see that actually the lowest energy state is not as low. And that reflects this destructive interference. And some time ago, Christian Baptiste actually realized that this can be turned into a very interesting argument about binding. He said, well, okay, that we know that like if we have a hole in a triangle moving in a spin polarized background, it's frustrated. But now let us assume that we have different spins. So now when the hole moves through the two trajectories, like the lower or the upper one, we end up with different spin configurations. And if we have different spin configurations, well, we no longer add the amplitudes, and therefore we don't have destructive interference. And so as a result, if one takes a system which is spin polarized, and then we introduce one flip spin, a magnon, and one hole, they will actually be bound to each other, because next to a magnon, the hole can propagate more efficiently. And the binding energy is really large. It's as large as like 6 times tunneling. So we get kind of binding between magnon and a hole, which is not related to super exchange energy. And this is actually closely related to the work that was done by Harter and Shastri, who started by who were motivated to just generalize the analysis by Nagaoka to triangular lattices, and realized that in the limit when U is infinity, a hole moving in a triangular lattice creates and kind of the anti-ferromagnetic state. Of course, in triangular lattice, we cannot have this up, down, up, down, up. It's 120-degree type state, which we would get for let's say anti-ferromagnetic Heisenberg model. Okay, so now what one can do is just, okay, let's study this regime of U equal to infinity, and let's ask indeed what kind of spin correlations will doping introduce. So here what was done by Ivan, so we take this model, right, in which basically no superexchange, we introduce either a hole or a doublet, and we ask what kind of spin correlations will appear next to this carrier, but we're no longer looking at the spin polarized system. Now we're sort of in the more familiar regime, like spin balanced system, but we're asking, well, if the hole can lower its kinetic energy by being in an anti-ferromagnetic environment, will it sort of favor having up-down configurations around itself? And indeed, you can see that these correlations, and these are now 3-point correlations, right? Because it's kind of a correlation function of two spin next to a hole. And you can see that the anti-ferromagnetic correlations develop at really high temperature, right? Sort of something which scales like a few times T. On the other hand, when we change doping from hole to doublon, then we no longer have this minus sign, right, when we go from electrons to doublons, and therefore we're in the domain of traditional Nagaoka physics, and the spin correlations which are induced by the doublon are ferromagnetic. Okay, so then what you can do, you can, again, in the regime of u over t equal to infinity, ask what would be spin susceptibility, and we're looking at, and you can ask, oh, is it actually a physical regime? So in the case of TMDC, if you look at relevant parameters, like the ratio of u over t is larger than 100, like 120, some maybe even 150. It's just because of the giant size of the supercell, and that's why starting to analysis from u equals infinity limit is not so unreasonable. And so now we can study this model at finite doping. So here what was done was just analysis of cylinders, like using the MRG, finite width, like 4. And one can then write susceptibility in exactly this Curie form and compute theta as a function of doping. And just as we would expect, exchange is equal to 0, so exactly at half filling. So epsilon is doping. We see no theta is equal to 0, no magnetic interaction. But when the system is doublon doped, we see ferromagnetic interactions. And when it's hole doped, we see anti-ferromagnetic interactions. And there is another interesting physics related to this kind of binding between holes and flipped spins. This is magnetization plateaus. It's easiest to explain starting from large fields. We start with a fully polarized magnetic system. We introduce a hole. And now we start reducing the field. And then what will happen is okay, as long as field stays large, flipping the spin costs energy, but the hole can benefit if there is a flipped spin next to it. So at some point, there will be a transition when each hole actually grabs, creates a magnet next to itself, and therefore magnetization as a function of magnetic field is not a smooth function, but it has this plateau, which basically corresponds to holes sort of binding magnons. And this is exactly what was seen in Cornell's experiments on the hole-doped side. What you can see is magnetization indeed exhibits these plateaus. However, these plateaus disappear on the doublon-doped side. Okay, so can quantum simulators shed some light on this? Well, hopefully we'll hear more from Wasim that they actually used their triangular lattices to really look at, this kind of most important correlators for this kinetic magnetism, which is 3-point correlators. So when they introduced holes, they show that the system develops anti-ferromagnetic correlations next to the hole. And when they introduced doublons, they saw ferromagnetic correlations. Again, this is color coding of 3-point correlations. And hopefully we'll hear more from Wasim later. And this is results from Marcus Greiner's group, where they're looking at the doublon-doped site and they increase interactions. And you can see that for weak interactions, the ferromagnetic kind of rigid ferromagnetic bubble, like Nagaoka polaron, is small, but then it gets larger. Okay, so, and then actually there is interesting physics which has to do with interaction between polarons. I don't have time to talk about it, but I'll be happy to talk offline. There is effective attraction between the polarons. But now what I want to switch to is experiments with Rydberg arrays, because, okay, what is left what has not been seen experimentally here is exactly this kind of bound state, like that the hole and the magnon can bind to each other. And so this is the challenge that the group of Antoine Bravet decided to address. So they use Rydberg excitations. Probably everybody heard about it. These are basically electrons excited to very high kind of quantum numbers. So we can think they have very large dipolar moments. And the type of physics that Rydberg physics which we're looking at is not really kind of going from the ground state to an excited Rydberg state, but rather between two highly excited states, which one is has L equals 1, the other has L equals 0, so there is an electric dipolar element between them. And because like the size of the orbitals is so large, it's a very strong dipolar interaction. So at distances even of 5 micron, there is huge dipolar interaction. And specifically, one can start in a configuration in which, say, one atom is in the p state, the other is in the s state, and because of dipolar interaction, they will flip, right? And that will look as some kind of exchange if we think about it as a two-level system. But in fact, they did something better, and this idea came from Lucas Homeyer. They actually introduced 3 states of the Rydberg. So here you can see, so there is one p state which corresponds to the hole, and then there are 2 s states which we can think of as spin up and spin down. And now, if we think about the spin flip between the S state, which corresponds to spin up, well, this really looks like tunneling of the spin up particle. Or if we think about this kind of exchange process, which corresponds to spin down state, well, this looks like a tunneling of the spin down particle. So effectively, we get a system in which we do not have double occupancies, but we have and we have tunneling, and there are 3 states. So it's a bosonic TG model. Okay, so since time is short, I'll just give you some highlights. So they started by preparing a zigzag ladder and initialized a magnon and a hole. And then they let them go. And actually, in this case, like exchange interaction can be neglected. So it's also basically like corresponds to infinite U. And what you can see in these plots is basically after they initialized this hole and magnon configuration, and then what's plotted is kind of distribution functions, coordinates of the hole and the magnon. And you see that they are spreading out, but you can see that essentially they are always next to each other. So as a hole moves, like the magnon is always next to it. Therefore, the state propagates as a bound state, right? They don't move separately, but they move together. And this just shows that the center of mass indeed expands, which shows that they're not just stuck together because they're prepared. Both of the hole and magnon expand, but they expand together. And then they have done similar experiments in 2D, again, prepared a hole and the magnon. And oh, and I forgot to tell you, obviously, like, so you remember for this effect to happen, the hole has to have like a negative sign of tunneling. So in this case, it just has to do from the fact that this exchange interaction between the hole and spin down has a minus sign because of dipolar interaction, because it's like effectively negative dipolar interaction. So fundamentally, it's kind of, even though we start in the hole-like state in the bosonic system, but its tunneling is the same as if this was a hole in a Fermi system. It naturally has a minus sign. Okay, so here you can see binding in 2D that, again, center of mass expands, but if after some expansion, we look at, again, where the magnon is relative to the hole, they're staying together. Okay, well, maybe I'll just... One can also look at higher bound state. In this case, they prepared 1 hole and 2 magnons and let this object expand in a ladder. And again, now we can look at correlations between the coordinates of a hole and a magnon or 2 magnons. And you see that 2 magnons are also traveling together because they are part of now this bound state of 3 particles, which again, and I remind you again, no magnetic interaction. The only reason magnons are staying together is because it's the best state for the hole to move. It's really kind of this binding arises from kinetic motion of the hole. And in this case, they also measured spin correlations around the hole, and you can see that that's when the hole moves, it develops antiferromagnetic correlations around it. It's a spin back. Okay, I know I'm stretching the patience, Randy. But just to highlight, so they can also, they prepared a 2-dimensional system. They started again with 1 hole and let the hole expand and see that as it expands, it actually develops exactly this 120-degree type correlations. On the other hand, they also have a way of basically changing the sign, which turns it into a doublon. And when a doublon expands, doublon-like dynamics, it actually creates ferromagnetic interactions. So here they can also see how this kinetic mechanism depends on effectively what we call hole or doublon doping and changes from ferromagnetic to antiferromagnetic. Okay, so with this, I want to conclude, I sort of told you about kinetic magnetism starting from the old work of Nagaoka and how it's relevant to this new Moire systems and the new insight that's coming from quantum simulation, both quantum gas microscopes and Rydberg arrays. Thank you.
All right, thanks very much, Eugene. Julian?
So, beautiful part. So I wonder how much implication there is for the overall phase diagram when you consider U to be reduced. And the reason I'm asking is because, you know, the latest Cornell experiment, same group, has shown a phase diagram for superconductivity, etc., that looks awfully similar to the square lattice case, and maybe there's some aspect of what you said that influences it.
So I sort of briefly mentioned that an obvious question to ask is, let's say if I have two dopants, will these dopants attract each other by sharing magnetic cloud, magnetic polaron? The answer is yes, you actually get bound states. But if you take plain vanilla, say TJ Hubbard model, this attraction is too strong. We find phase separation. So we have to look at physics beyond TJ and Hubbard. So for the TJ lighters, let's say for double doping, we actually we looked at the phase diagram. It's very rich. It has very different types of incommensurate order, but it also has phase separation regimes. So like how to turn phase up, and you can say clearly for systems with long-range interaction, phase separation should not occur. So we should include other things like long-range Coulomb, which is perhaps will preserve pairs, but will not allow these pairs to start clustering together. But say with the MRG, it's harder to study. So I think we have strong indication that this kinetic magnetism is a driving force for pairing, but it's at least this, plain vanilla Hubbard J are not enough to explain the phase diagram.
Okay, one last question, Han.
What would you mean bound? I mean, they just localize together, right? So it's they prepared, like, it's very simple factorizable state because they can have local manipulation. So basically, by using local ASIS shifts and global addressability, they can flip kind of spins locally, start with everything polarized and flip one of the spin to make a hole, flip another to make a magnon. So, I mean, they're not bound, they're just created next to each other. And then dynamics occurs according to this TGA, Bosonic TGA model.
I think that we could talk for a long time about the very deep physics that you've discussed here, but I think we've run out of time. I'm looking at you, Chimio. Okay, so I have one question then. So is there a actual phase transition in the Nagaoka system? So if you on a square lattice, you turn up U over T to be infinite. Do a phase transition in there?
So for the square lattice, yes. So basically, you can. So it's more like a sharp crossover, right? So if you start introducing a dopant in a square lattice, then you know that beyond, if U is large, but U over T has to be outrageously large, like also like 100 to 20 or something, then this hole actually dresses itself in this fermionic, in this ferromagnetic kind of Nagaoka cloud. So for triangular lattices, you also get this ferromagnetic. For the double doped side, say, like you can also get this ferromagnetic polarization cloud, but at much weaker interactions.
All right, thanks very much.